So now we are going to discuss about the single phase full bridge inverter. So single phase full bridge inverter we are going to study in a very detailed manner. Suppose the circuit is going to look like this, which is plus or minus VDC by 2 plus or minus VDC by 2. I am going to assume this as a neutral position or the ground potential, which is 0. So this is a switch S1 and switch S2, switch S3 and switch S4. So we are going to keep a diode also in parallel with them. So D1, D2, D3 and D4. So now I am going to keep the load between these two legs. So between these two legs I am going to keep a load, which is, it can be any type, load can be any fashion. So the load voltage is plus or minus V naught of T and the load current is I naught of T. So now we are going to analyze this circuit. Let me take 2 points A and B and then I am going to analyze this circuit. Analysis of the circuit, which is VA0 and VB0. So VA0 and VB0 are called as the pole voltages. So VA0 and VB0 are called as the pole voltages, whereas VAB is called as the line voltages. So listen carefully. VA0 and VB0 are called as the pole voltages, whereas VAB is called as the line voltage, or simply we can say the voltage across the load. So VAB is equal to VA0 minus VB0. So VA0 and VB0 are called as the pole voltages and VAB is called as the line voltages, and VAB is equal to VA0 minus VB0. So now I am going to analyze for any load. So for any load, when S1 S2 are on, when the two switches S1 and S2 are on, so with the help of circuit diagram we can say that output voltage is greater than 0 and also the output current is also greater than 0. So this is the nature when S1 and S2 are on. Suppose when D1 and D2 are on, so what is going to happen? When D1 and D2 are on, then the output voltage is again positive, whereas the output current is negative. When S3 and S4 are on, so when S3 and S4 are on, so the output voltage is negative, whereas the output current is negative. Similarly, when D3 and D4 are on, the output voltage is negative and the output current is positive. So this is the nature of the voltage and current for different types of combination of the switches. So now I am going to analyze the circuit. So this graphs. So here, when first I am going to on the S1 S2. So when I on S1 and S2, then I have already told you the output voltage is equal to plus VDC. So the output voltage is equal to plus VDC. If you want VA0, which is equal to plus VDC by 2, whereas VB0, is equal to minus VDC by 2. So therefore you have to draw these plots. When S3 and S4 are on, then we can say V0 of T is equal to minus VDC, and V0 of T is equal, or simply we can say VAB is equal to minus VDC. Whereas VA0, is equal to minus VDC by 2, whereas VBO is equal to plus VDC by 2. So if you want VAB is equal to output voltage is equal to VA0 minus VB0. So if you do the subtraction of these two graphs, VA0 minus VB0, we are going to get this graph. So therefore VAB is equal to VA0 minus VB0, where VAB is called as the line voltage or the output voltage of the load, whereas VA0 and VB0 are called as the pole voltages. So from 0 to T by 2, S1, S2 are on, whereas T by 2 to T, S3, S4 are on, to get this type of voltage. So now I want to analyze the graphs. So VA0, the pole voltage VA0 is equal to sigma n is equal to 135 up to infinity 4 into the peak value, which is VDC by 2 by n pi sine of n omega naught t. So after solving this one, we are going to get sigma n is equal to 135 up to infinity 2 VDC by n pi sine of n omega naught t. And if you want to draw what is the Fourier transform or the Fourier series expression of the VB0 is equal to sigma n is equal to 135 up to infinity 4 into the peak value, which is VDC by 2 by n pi sine of n omega naught t minus n pi. So n omega naught t minus n pi. This is the way, it is going to delay by pi. It is going to delay by n pi. So therefore that is the thing that you are going to get for these things. So after simplifying, we are going to get sigma n is equal to 135 up to infinity 2 into VDC by n pi sine of n omega naught t minus n pi. So this is VB 0. So if you want output voltage is equal to VAB is equal to VA naught minus VB naught. So if you do these things, finally we are going to get sigma n is equal to 135 up to infinity 4 into the peak value which is VDC by n pi sine n omega naught t. So this is the expression that we are going to get the output voltage. And if you want to know what is the RMS value of the output voltage, our output voltage is equal to VAB. So its RMS value is equal to peak value which is VDC. So RMS value of the output voltage is equal to peak value which is VDC. So if you want to find what is the RMS value of the fundamental component of the output voltage. So RMS value of the fundamental component of the output voltage is peak value by root 2. So 4 VDC by pi by root 2. So if you solve this one, we are going to get 2 into root 2 by pi VDC. So this is called as the RMS of the fundamental component of the output voltage. So this is called as the RMS value of the fundamental component of the output voltage. So if you want to know what is the distortion factor for this output voltage, which is simply the RMS value of the fundamental component of the output voltage by the RMS value of the overall output voltage. So RMS value of the fundamental component of the output voltage is 2 into root 2 by pi VDC, whereas the RMS value of the overall output voltage is VDC. So if you do the two things division, finally we are going to get 2 into root 2 by pi, which is called as the 0.9. So distortion factor of this output voltage is equal to 0.9, whereas THD is equal to under root over 1 by g whole square minus 1. So in place of g, if you substitute 0.9 and you do simplification, finally we are going to get 0.483 is the THD we are going to get. So now we are going to study for R load. So we are going to now specifically we have to apply the load as R load for the single phase full bridge voltage source inverter. So this is plus or minus VDC by 2 plus or minus VDC by 2. So overall input voltage is now VDC. And this is a circuit diagram which is S1, S2, S3, S4 with their parallel switches D1, D2, D3, D4. So we are going to keep a load which is R load and the output voltage is plus or minus V naught of t and the output current is I naught of t. This is called as the source current. IS is the source current. And this is called as the switch current, which is the current through the switch, any of the switch. I am going to assume switch as S1. So therefore, the current of the switch is ISW. So now we are going to do the analysis of this circuit. So now we are going to do the analysis of the circuit, which is I01 of t is called as the fundamental component of the output voltage. So I01 of t is called as the fundamental component of the output current. Whereas ISW01 of t is called as the fundamental component of the switch current, switch S1 current. So we are going to discuss only the switch S1. So simply we can say that I01 of t is called as the fundamental component of the output current, whereas ISW01 of t is called as the fundamental component of the switch S1 current, the fundamental component of the switch S1 current. I have already told you for any load, when S1, S2 are on, I have already told you the output voltage is a positive and the output current is also positive. Whereas when D1, D2 are on, I have already told you the output voltage is again positive, whereas the output current is negative. Similarly, when S3, S4 are on, then I have already told you the output voltage is a negative and the output current is also negative. Whereas when D3, D4 are on, I have already told you the output voltage is negative, whereas the output current is positive. So this is the thing that you need to always be remembering these concepts. So now I have already told you for 0 to t by 2 the output voltage is equal to plus VDC, whereas from t by 2 to t the output voltage is a minus VDC. So they are going to get, this is the output voltage irrespective of the load, you are going to get this graph only. So irrespective of the load you are going to get this graph only, but only thing the output current is going to change based on the load elements. So here it's a pure resistive load, so therefore the waveform of the output voltage and the output current are same. So from 0 to t by 2 the output current is the output voltage by R, which is plus VDC by R, whereas from t by 2 to t the output current is equal to output voltage by R, which is minus VDC by R. So this is the thing that you are going to get, the graph of V0 and I0. So now I am going to write the Fourier series expansion of this output voltage, which is equal to sigma n is equal to 135 up to infinity 4 into the peak value, which is VDC by n pi into sine of n omega naught t. and I want to know what is the value of the current I naught of t is equal to sigma n is equal to 135 up to infinity 4 VDC by n pi r into sine of n omega naught t. So this is the output current we are going to get. So now I want to find what is the fundamental component of the output voltage, which is, yes, substitute n is equal to 1, we are going to get 4 VDC by pi sine omega naught t. Similarly, I want to find what is the fundamental component of the output current, is equal to substitute n is equal to 1, we are going to get 4 VDC by pi r into sine omega naught t. So we got the fundamental component of the output voltage and the fundamental component of the output current. Then I want to find what is the RMS value of the overall voltage, is equal to peak value, which is V plus VDC, whereas the RMS value of the fundamental component of the output voltage is, so this is the peak value by root 2, we are going to get 2 into root 2 by pi VDC. Similarly, I want to find what is the RMS value of the fundamental component of the output current. So this is the peak value by root 2, we are going to get 2 root 2 by pi r into VDC. So now I want to find what is the maximum value of the fundamental component of the output current, is equal to 4 VDC by pi r. So this is the thing that we are going to get. So now I am going to draw the graph of the fundamental output current. So fundamental output current is, just now we have discussed, is 4 VDC by pi r into sine omega naught t. So we are going to get in this fashion. So this is the graph we are going to get, which is 4 VDC by pi r into sine omega naught t. So this is the graph we are going to get with the peak value, which is 4 VDC by pi r. So this is the thing we are going to get. I have already told you from 0 to t by 2, S1, S2 are on, and from t by 2 to t, S3, S4 are on. So now I want to find what is the average switch current and the RMS switch current. I want to find what is the value of the average switch current and the RMS switch current. So switch current, see, switch current is here S1. See, S1 is on only from 0 to t by 2, and the remaining region it is off. So in that period, whatever the switch current is equal to the output current, so therefore which is equal to VDC by R from 0 to t by 2, and the remaining range is equal to 0. So this is the switch current we are going to get. I want to find what is the average value of switch current, which is area by overall time period, VDC by R into t by 2 by t, we are going to get VDC by 2R. Similarly, I want to find what is the RMS value of switch current, which is VDC by R into under root over t by 2 by t, we are going to get VDC by root 2 into R. So this is the thing that we are going to get. So this is the average value of switch current and the RMS value of the switch current. Similarly, I want to find what is the average source current and the RMS source current. Similarly, I want to find what is the average source current and the RMS of the source current. So source current, you can see clearly the source current is equal to, the source current is equal to, see, during S1, S2. So during 0 to t by 2, S1, S2 are on. So during 0 to t by 2, S1, S2 are on. So therefore the source current is equal to load current. So whatever the load current is equal to source current, which is plus VDC by R. From t by 2 to t, S3, S4 are on. S3 and S4 are on. So therefore whatever the output current is negative of the source current, is the negative of the source current. So therefore source current is the negative of the output current. So we are going to get here plus VDC by R. So we are going to get a straight line for all the time, which is equal to VDC by R. So average value is equal to peak value, and RMS value is also equal to peak value, which is VDC by R. So now I want to find what is the fundamental power across the load, means how much amount of fundamental component of the power is absorbed by the load. So the fundamental component of the active power across the load is equal to RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current into cos of, whereas phase angle between the fundamental component of the output voltage and the fundamental component of the output current is phi1. So cos phi1 is equal to cos of phase angle between the fundamental component of the output voltage and the fundamental component of the output current. They are always in phase because of resistive load. So 0 degree, so cos 0 is equal to 1. So therefore the fundamental component of the output power is equal to V01 RMS into I01 RMS, or simply we can say V01 RMS whole square by R is equal to I01 RMS whole square into R, because we already know what is the RMS value of the fundamental component of the output voltage. We can substitute here. Similarly, we also know what is the fundamental component of the RMS value of the, means we know what is the RMS value of the fundamental component of the output current. You can substitute even that value. So finally, if you do the simplification, we are going to get 8 VDC square by pi square R. So this is the amount of this much amount of total fundamental power is consumed by the load. Then what is the fundamental power delivered by each source? So fundamental power delivered by each source, how much is the thing that we need to figure out. So in order to do this one, first we have to find what is the fundamental component of the source current. What is the fundamental component of the source current we need to figure out. So fundamental component of the source current we need to figure out. So simply we can say that here, which is here, see IS01 of t is called as the fundamental component of the source current. Fundamental component of the source current. So now you can see clearly here from 0 to t by 2, from 0 to t by 2, I have already told you the output current is equal, as S1 and S2 are on, so therefore the source current is equal to output current. So simply the fundamental component of the output current is equal to fundamental component of the source current. So we are going to get like this. So we are going to get like this. This is the thing we are going to get with a 4 VDC by pi r. Whereas from t by 2 t, I have already told you S3, S4 are on. So therefore the source current is negative of the load current. So negative of the load current means simply the source current in the fundamental component of the source current in this region is equal to negative of the fundamental component of the output current. So you are going to get like this. Actually output current is negative, the fundamental value is negative, but you have to go negative and negative. So therefore you are going to get positive. So now I want to find what is the amount of, what is the fundamental power delivered by each source I want to figure out, which is VDC by 2 into the average value of the fundamental component of the source current. So VDC by 2 into average value of the fundamental component of the source current. So VDC by 2 into, so this average value is equal to 2 into peak value by pi. So 2 into peak value by pi. So we are going to get like this. So this much amount of fundamental, this much amount of fundamental power is supplied by each source. Then what is the total power across load? What is the total power across load? So total power across load means how much amount of active power consumed by the load, which is equal to V0 RMS, means RMS value of the output current into RMS value of the output current into cos of phi. Because that is a pure resistive load, so both are in phase. So therefore cos phi is equal to 1. So therefore P is equal to V0 RMS into I0 RMS, or simply we can say V0 RMS whole square by R, or is equal to I0 RMS whole square into R. So here I have already told you V0 RMS value is equal to VDC. So if you substitute here, we are going to get VDC square by R. So this much amount of active power is consumed by the load. Then what is the total power delivered by each source? So total power delivered by each source is equal to, total power delivered by each source is equal to, so total power delivered by each source, I want to find what is the total power delivered by each source is equal to VDC by 2 into the average value of the source current. So VDC by 2 into the average value of the source current is equal to VDC by R. Just now we have discussed. So we are going to get VD square by 2R, or simply we can say that this is the VD square by 2R. So simply we can say that the total power consumed by the load is equal to 2 times the power delivered by each source. So listen carefully. The total power consumed by the load is equal to 2 times the total power delivered by each source. Similarly, the total fundamental power absorbed by the load is equal to 2 times the total fundamental power delivered by each source. So I already told you the source current is always VDC by R for all the time. So switch current. So if you want to find what is the switch current fundamental means fundamental component if you want to figure out. So ISW01 of t is called as the fundamental component of the switch current. I have already told you from 0 to t by 2 the S1, S2 are on. So therefore the switch current is equal to load current in this region. So simply we can say that in this region, so whatever the fundamental component of the output current is equal to fundamental component of the switch current. So we are going to get like this. This is the graph we are going to get. But from t by 2 t, switch S1 is open. So therefore its current is equal to 0. So its current is always equal to 0. So this is the fundamental component. This is the fundamental component of the switch current. So we are going to get like this. So now we are going to study about the inductive load. So here we are going to replace the resistor load by the inductive load in the single phase full bridge voltage source inverter, and then we are going to analyze this circuit. So this is VDC by 2. This is or we can say ground potential or the neutral point, or we can say a reference node. So this is switch S1 and switch S2, switch S3 and switch S4. So diode D1, D2, D3 and D4. So this is the inductor we are going to keep, and the load voltage is plus or minus V0 of t, and the load current is I0 of t. So now we are going to analyze this circuit. As I've already told you, from 0 to T by 2, its output voltage will be always equal to supply voltage, which is VDC. Whereas from T by 2 to T, I've already told you the output voltage will be minus VDC. So irrespective of the load, always this is the category we are going to get. This is the output voltage we are going to get. But the only thing is the output current is going to get changed. I have already told you, whenever you give a DC supply to the inductor, the current is going to get like a simply ramp signal. So because as it is a pure inductive load, so the current is going to lag the supply voltage by 90 degree. So therefore, so by T by 4 means this is the current you are going to get. So this is the current you are going to get T by 4, T by 2, 3T by 4 and T. So it is going to be lagging the supply voltage by 90 degree. So this is the maximum value of the output current, and this is also minus I naught max, and this is plus I naught max. So this is the thing that you are going to get. So you can see clearly now. I've already told you one important point, the concept which is from 0 to T by 2, here voltage is positive and the current is negative. So as the out in the 0 to T by 4, the output voltage is positive and the output current is negative. Then simply we can say here D1, D2 are on. Whereas from T by 4 to T by 2, both are positive. Output voltage is positive and the output current is positive. It indicates that S1, S2 is on. Whereas from T by 2 to 3T by 4, here output voltage is negative but the output current is positive. This is only when D3, D4 are on. Similarly, when 3 by T by 4 to T, the output voltage and the output current both are negative. This is possible only from when S3 and S4 are on. So now we know the ranges where the which switch is on. So now I am going to do the analysis of this circuit. So for any load, I have already told you when S1, S2 are on. So when S1 and S2 are on, I have already told you which is the output voltage is positive and the output current is also positive. Whereas when D1, D2 are on, the output voltage is positive but the output current is negative. When S3 and S4 are on, the output voltage is negative whereas the output current is also negative. When D3, D4 are on, the output voltage is negative whereas the output current is positive. So this is the thing that you are going to get. So based on this, we have DT for which range which switches are on. I have already told you. Because from 0 to T by 4, D1, D2 are on. From T by 4 to T by 2, S1, S2 are on. And from T by 2 to 3T by 4, D3, D4 are on. And from 3T by 4 to T, S3, S4 are on. So we can see clearly here from 0 to T by 4, D1, D2 are on. Whereas from T by 4 to T by 2, S1, S2 are on. Whereas from T by 2 to 3T by 4, D3, D4 are on. And whereas from 3T by 4 to T, S3, S4 are on. So this is the range of switches they are going to conduct. Based on the output voltage and output current, we have know the switching of these things. DC voltage across inductor, the current is triangular and it lags by 90 degree or TT by 4. I have already told you, when you apply a DC voltage across the inductor, the current is basically a ramp signal, but as a ramp signal, it is going to lag the supply voltage by 90 degree. So for a DC voltage across inductor, the current is a triangular and it lags by 90 degree or T by 4. And if you want to know what is the RMS value of the output voltage, which is the peak value, which is VDC. So if you want to know what is the conduction angle of each diode, the conduction angle of each diode is only conducting for only pi by 2 or T by 4 time. So conduction angle of each diode and each thyristor is only for pi by 2 or T by 4. Only this much amount of time or this much amount of angle range only they are conducting. So conduction angle of each diode is equal to the conduction angle of each thyristor is equal to, which is T by 4 or pi by 2. Whereas conduction angle of all diodes, the conduction angle of all diodes is equal to conduction angle of all thyristors. All diodes are going to conduct means D1, D2, D3, D4. If you take everything, they are going to conduct for only pi degree or T by 2. So therefore pi or T by 2. Similarly, the conduction angle of all thyristors or all diodes is only, which is again same, pi or T by 2. So if you want to know what is the average switch current and the RMS value of switch current. So basically if you want to find what is the average value of switch current and the RMS value of the switch current. So now I have already told you S1, S2 are on only from T by 4 to T by 2. So now I am going to assume a switch current ISW is called as the current in the switch which is flowing in the switch S1. So switch S1 is on only from T by 4 to T by 2. Only in this range the switch S1 is on. So therefore, whenever the switch S1 is on, the output current is equal to the current in the switch. So therefore, it is going to follow the load current. In the remaining time it is open. So therefore, current is equal to 0. So this is the thing that we are going to get for the switch current. And if you want to know what is the diode current, what is the diode current if you want to figure out. So I am going to find the diode current in this range from the D3 to D4. So D3 D4 are going to conduct. Let me take diode D3. So for D3 I want to find what is the value of the diode current. So as D3 is connecting only from T by 2 to 3T by 4, in the remaining range it is off, so it is 0. And whenever the D3 is connecting, whatever the current in the D3 is equal to current in the load, so it is going to blindly follow the load current. So this is the thing that we are going to get. So based on this, I want to find what is the average value of the switch current and the average and the RMS value of the switch current. So average value of the switch current is equal to area of into I naught max into T by 4 by capital T. So you are going to get I naught max by 8. Similarly, if you want to find what is the RMS value of the switch current is equal to under root over 1 by 2 pi integration of 0 degree to 90 degree. The means the slope is nothing but here I naught max by here we are say I naught max by pi by 2. So I naught max by pi by 2 into theta whole square into d theta. So finally you are going to get I naught max by root 12. So I naught max by root 12 you are going to get. And if you want to find what is the fundamental component of switch current and the average and RMS values. So if you want to find what is the average and RMS value of the fundamental component of the switch current. So finding out the average and RMS value of the fundamental component of the switch current if you want to figure out. So if you want to find what is the average and RMS value of the fundamental component of the switch current. So I've already told you here, listen carefully. Before this, let me discuss this simple concept. See, let me do the Fourier series of the output voltage and the output current because they are periodic signal. So output voltage is equal to sigma n is equal to 135 up to infinity 4 into the peak value which is VDC by n pi sin n omega naught t. So if you want the output current which is equal to output voltage by XL is equal to sigma n is equal to 135 up to infinity 4 VDC by n pi into n omega naught L. So you are going to get 4 VDC by n square pi omega naught L sine of n omega naught t minus n pi by 2. If you take n common, you are going to get in this fashion. So XL is equal to n omega naught into L. So if you want to find what is the maximum value of the fundamental component of the output current is equal to substitute n is equal to 1, we are going to get 4 VDC by pi omega naught L. So simply we can also call as the maximum value of the fundamental component of the output voltage by omega naught L or n omega naught L. So it's the ratio of the maximum value of the fundamental component of the output voltage by n omega naught L. When n is equal to 1, we are going to get this value. So this is called as the fundamental component of the, or we can say our maximum value of the fundamental component of the output voltage or output current. So now based on this, we are going to analyze few more important things. See, I have already told you fundamental component, or you can say the average and the RMS value of the fundamental component of the switch current. This is what I want to figure out. See, one more important thing is here. I want to find this value, right? So here the switch current, or we can say switch, the average value of the fundamental component of the switch current. So if you want to figure out this one, it's very simple because for T by 4 to T by 2, switch S1 is connecting and in the remaining ranges, switch S1 is absent. So only in this range, the fundamental component of the switch current is equal to fundamental component of the output current only in this range. So therefore, only in this range it will be possible, and in the remaining ranges it is not at all possible. So first thing is we are going to draw what is the fundamental component of the output current. So fundamental of the fundamental component of the output current, just now we have told you there is an expression we are going to get in this manner. So this is the we are going to get. So this is the I01 max. It is called as the maximum value of the fundamental component of the output current. So now I want to find what is the fundamental component of the switch current. I have already told you from T by 4 to T by 2, only in this range S1 is conducting. So whatever the fundamental component of the output current in this range is equal to fundamental component of the switch current. So it is going to follow this value. Similarly, in this D3, D4 is conducting from T by 4 to 3T by 4. So then as D3 is conducting, whatever the diode current D3 is equal to current in the output load. So therefore simply we can see that in this range the fundamental component of the diode current is equal to fundamental component of the output current in this range. So it is going to follow this graph. So now we are going to find what is the average and the RMS value of the we are going to find what is the average and RMS value of the fundamental component of this switch current and also this diode current we are going to figure out. So we can see clearly the average and the RMS value, of the fundamental component of the switch current is equal to the maximum value by 2 pi, because I have already told you this is called as the half of the half wave rectifier. It is basically half of a half wave rectifier. So therefore for half wave rectifier, peak value by pi, it is half of a half wave rectifier bits again by 2. So I dot max by 2 pi is the thing we are going to get. If you want to find what is the RMS value of the fundamental component of the switch current, it is equal to, I have already told you, for a half wave rectifier the RMS value is peak value by 2, but here it is half of the half wave rectifier, so divided by again root 2. So therefore you are going to get I naught 1 max by, this is I naught 1 max by 2 into root 2. So this is basically I naught 1. It means that here I naught 1 max is called as it is a maximum value of the fundamental component of the output current, or we can say it is called as the maximum value of the fundamental component of the output current. So this is called as the maximum value of the fundamental component of the output current by 2 into root 2. So this is called as the RMS value of the switch current. So same thing is going to hold for even diodes because the graphs are same. So therefore simply we can say that the average value of the fundamental component of the switch current is equal to average value of the fundamental component of the diode current. Similarly, the RMS value of the fundamental component of the switch current is equal to RMS value of the fundamental component of the diode current. So both are again same. So now we are going to find what is the fundamental displacement factor, which is cos phi 1. Phi 1 is the angle between the phase angle between the fundamental output voltage and the fundamental output current. As you can see clearly, the angle between them is nothing but 90 degree. So therefore cos 90 is equal to 0. So fundamental displacement power factor is equal to 0. So fundamental output active power. So what is the amount of fundamental active power absorbed by the load? Only the fundamental output power. Fundamental output active power absorbed by the load is equal to RMS value of the fundamental output voltage into RMS value of the fundamental output current into cos of phi 1, where phi 1 is the angle between the fundamental output voltage and the fundamental output current. As phi 1 is equal to 90, so cos 90 is equal to 0. So anything is again 0. So therefore the fundamental output power consumed by the load is equal to 0. Similarly, the fundamental output reactive power consumed by the load is equal to the RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the load current into cos of sine of phi 1, where phi 1 is the phase angle between the fundamental output voltage and the fundamental output current. As phi 1 is equal to 90, so sine 90 is nothing but 1. So we are going to get RMS value of the fundamental component of the output voltage into RMS value of the fundamental component of the output current. So if you want to find these values, so the RMS value of the fundamental component of the output voltage, just now we have figured out it is 4 VDC by root 2 into pi. Similarly, if you want to find what is the RMS value of the fundamental component of the output current, which is again simply you have to go like this, again 4 VDC by root 2 pi omega naught L. So these things that you can get from the expression of the output voltage and the output current. So if you want to find what is the maximum inductor current, is very simple. Here, see, from 0 to t by 2. So from 0 to 2 by 2, the output voltage is equal to plus VDC. So therefore, as the output voltage is equal to plus VDC, by using the voltage and current relationship across the inductor, so V naught is equal to L di by di naught by dt. Because V naught is called as the inductor voltage. So therefore, inductor voltage is equal to, in this range, is equal to plus VDC. So therefore, plus VDC is equal to L. Plus the amount of change. The amount of change in this region is 2 I naught max by time period is t by 2. So therefore, if you solve this one, we are going to get I naught max is equal to VDC into t by 4L. So this much amount of maximum current you are going to get in this range. So from 0 to t by 2, capital T by 2, the output voltage is equal to plus VDC. So therefore, plus VDC is equal to L into the amount of change, which is 2 I naught max by 2 I naught max. So 2 I naught max by, simply we can say t by 2. So if you solve this one, we are going to get I naught max is equal to VDC into t by 4L. So this is the value that we are going to get. And always remember one thing, the fundamental component, or you can say that the maximum value of the fundamental component of the output current is always lesser than the maximum value of the output current. Listen carefully. Always the maximum value of the fundamental component of the output current is always lesser than the maximum value of the overall output current. Now we are going to learn about the RL load. So now we are basically learning about the RL load. So in the previous we have learned about the L load, but now we are going to discuss about the RL load. So this is the circuit diagram. VDC by 2, VDC by 2. So this is the load RL. And the load voltage is plus or minus V naught of t, and the load current is I naught of t. The switches are S1, S2, S3 and S4, and the diodes are D1, D2, D3 and D4. Now we are going to basically analyze this circuit. So irrespective of the load, the same voltage we are going to get, which is from 0 to t by 2, the output voltage is plus VDC, whereas from t by 2 to t, the output voltage is minus VDC. As I have already told you, it is a RL load. As it is a RL load, if you are going to give any DC supply to this RL load, it will be exponential. The current will be exponential. So therefore, but the current is going to lag the supply voltage by some angle phi 1. So this is the thing that you are going to get. So this is the like increasing and then decreasing. So if this is phi 1, then this will be pi plus phi 1. So therefore we can say this is I naught max and this is minus I naught max. The maximum, we can say the maximum value of this output current is I naught max and minus I naught max. So now, so you can see clearly from 0 to pi 1. So 0 to pi 1, the output voltage is positive and the output current is negative. See, whenever the output voltage is positive and the output current is negative, I have already told you very simple, that is D1, D2 are conducting. Similarly, from pi 1 to pi, from pi 1 to pi, you can see the output voltage is positive and also output current is positive. So both are positive means S1, S2 are on. So from pi 1 to pi, S1, S2 are on. Similarly, from pi to pi plus pi 1, the output voltage is negative, whereas the output current is positive. So output voltage is negative and the output current is positive means D3, D4 are going to connect in this region. Similarly, from pi plus pi 1 to 2 pi, the output voltage is negative and the output current is negative. So both are negative. It indicates that S3, S4 are conductive. So based on this, we have known which device are going to conduct for which amount of range. So same thing is that you can see clearly from 0 to pi 1, D1, D2 are conducting. From pi 1 to pi, S1, S2 are conducting. From pi to pi plus pi 1, D2, D4 are conducting. And similarly, pi plus pi 1 to 2 pi, S3, S4 are conducting. Same thing that I have told you. So now we are going to do some more analysis of this circuit. So for any load, I have already told you, for any load, when S1, S2 are on, I have already told you, whenever the S1, S2 are on, so the output voltage is positive and also the output current is also positive. Whenever D1, D2 are on, the output voltage is positive and the output current is negative. Whenever the S3, S4 are on, the output voltage is negative, whereas the output current is also negative. Whenever the D3, D4 are conducting, the output voltage is negative and also the output current is positive. So these are the things that we are going to get from the circuit itself. And whenever DC voltage is applied across the RL load, then the current is exponential and it lags by phi 1. This is a very important point. This is the thing I have already told you. Whenever you apply any DC voltage across the RL load, the current is exponential. As the RL load, the current should lag. So the current is going to lag the supply voltage by some amount of angle phi 1. So when DC voltage is applied across RL load, then the current is exponential and it lags by phi 1. And the RMS value of the output voltage is equal to, and the RMS value of the output voltage is equal to, see, the RMS value of the output voltage is equal to, which is the peak value itself, which is VDC. So the RMS value of the output voltage is equal to VDC. Whereas you can see clearly what is the conduction angle of each diode. Each diode is going to conduct for only phi 1. So the diode is going to conduct for only phi 1. Whereas each thyristor is going to conduct for pi minus phi 1. This we can obtain from the graph itself. So the conduction angle of each thyristor is phi 1, whereas the conduction angle of each diode is phi 1, whereas the conduction angle of each thyristor is pi minus phi 1. Now we are going to use the Fourier series. As the output is a pure is a periodic signal, so we can get the Fourier series expansion, which is v naught of t is equal to sigma n is equal to 135 up to infinity 4 VDC, 4 peak value VDC by n pi into sine n omega naught t. So I want to find what is the value of the current I naught of t is equal to sigma n is equal to 135 up to infinity 4 VDC by n pi mod of Zn sine of n omega naught t minus phi n. So n omega naught t minus phi n. So Zn is equal to under root over r square plus n omega naught l whole square, whereas phi n is equal to tan inverse of n omega naught l by r. So phi n is called as is equal to tan inverse of n omega naught l by r. It's a very important point. See, phi n is always equal to tan inverse of n omega naught l by r. It's a very important point. See, n is not outside, n will be always inside. This is the thing that we need to always be careful. So always phi n is equal to tan inverse of n omega naught l by r. It's a very important thing. N is always inside, but not the outside of the tan inverse. It will be always inside. So phi n is equal to tan inverse of n omega naught l by r. Fundamental displacement factor is equal to it is a cos of phase angle between the fundamental output voltage and the fundamental output current. So you can see clearly the fundamental output voltage and the fundamental output current, the phase angle is phi 1. So phi 1. So phi 1 is equal to, here in place of n substitute 1, we are going to get tan inverse of omega naught L by R. So this is the power factor angle. So fundamental displacement power factor is equal to cos of phi 1. So now I am going to draw what is the fundamental output voltage. The fundamental output voltage is, just now we have known, the fundamental output voltage is very simple. Substitute n is equal to 1, we are going to get 4 VDC by pi sine omega naught t. So this is the curve we are going to get. V1 naught max is called as the 4 VDC by pi. So therefore this is the fundamental output voltage graph we are going to get. Similarly, if you want to find what is the fundamental output current, fundamental output current means if you know the I naught of t, substitute n is equal to 1, we are going to get 4 VDC by pi into mod of Z1 sine of omega naught t minus phi 1. So basically this is the thing that you are going to get. This is the graph you are going to get. Basically this is the nature you are going to get. The maximum value is 4 VDC by pi of mod Z1. This is the thing that you are going to get. So this is the fundamental output voltage and the fundamental output current. So this is the graph that you are going to get. So now I want to find what is the switch current, the fundamental switch current. See, switch for the characteristic switch one I want to figure out. See, switch S1 is connecting only from phi 1 to P by 2. Only from phi 1 to phi only the switch S1 is conducting. So therefore, see, whenever the switch S1 is conducting, the output current is equal to current in the switch. So therefore, only in this region, in the remaining region, S1 is not conducting, means its fundamental current will be equal to 0. But only in this region, whatever the fundamental component of the output current is equal to fundamental component of the switch current. So therefore, see, it is going to follow blindly the output current, means the fundamental value of the output current in this range. So this is the thing that you are going to get. Similarly, for diode also, I want to find what is the fundamental component of the diode current also I want to figure out. See, only D3 is connecting from pi to pi plus phi 1 and the remaining range it is off, so 0. But from here, as the D3 is connecting, whatever the output current is equal to D3 current, so therefore the fundamental component of the load current is equal to fundamental component of the D3 current, so therefore you are going to get whatever the nature of the load current in this period, that means fundamental load current will be same as here also. So this is the thing that you are going to get. So now we are going to find what is the fundamental component of switch current average and the RMS value. Means we are basically find what is the value of the average and the RMS value of the fundamental component of the switch current. Fundamental component of the switch current. So fundamental component of the switch current means simply I have already told you ISW01 of the what is the average value and the RMS value we are going to figure out. So the average value of the fundamental component of switch current is equal to 1 by 2 pi integration of phi 1 to pi. In this region, the fundamental component of output current is I naught 1 max into sine of omega naught t minus phi 1 into d theta. Similarly, if you want to find what is the RMS value of the fundamental component of switch current is equal to and root over 1 by 2 pi integration of pi 1 to pi, here it is equal to the fundamental component of the output current is I naught 1 max sine of omega naught t minus phi 1 whole square into d theta. Similarly, I want to find what is the fundamental active power across the load. Means how much is the fundamental active power which is consumed by the load. So fundamental active power across the load is equal to RMS value of the fundamental output voltage into RMS value of the fundamental output current into cos of phi1. If phi1 is the saying the RMS value of the fundamental output voltage we have already discussed, which is 4 VDC by pi into root 2. Similarly, the RMS value of the fundamental output current is 4 VDC by root 2 pi into mod of J1. Now, we know each and everything, even cos phi1 also we know. Then we can substitute and we can do simplification to get the amount of fundamental active power consumed by the load. Similarly, fundamental reactive power across the load means how much amount of fundamental reactive power consumed by the load is equal to RMS value of the fundamental output voltage into RMS value of the fundamental output current into sin of phi1. Each and everything we know, just with the substitution and the multiplication, we are going to get the solution. So similarly, we are going to find what is the fundamental component of diode current average and the RMS value. So we are going to find what is the average and the RMS value of the fundamental component of the diode current. So the average value of the fundamental component of the diode current is equal to 1 by 2 pi integration of 0 to phi 1. So in this range, what is the current we are going to get? It is the current across the fundamental component of the output current, which is I01 max sin of omega naught t minus phi 1 dt. The RMS value of the fundamental component of the diode current is equal to same root over 1 by 2 pi integration of 0 to phi 1, the fundamental component of the output current in this range, which is I01 max to sin of omega naught t minus phi 1 whole square into d theta. So if you solve this one, we are going to get the RMS value and the average value of the fundamental component of the diode current. Suppose if the load is highly inductive, what is going to happen? If the load is highly inductive, means the resistance is very, very less, so current will be almost constant. So therefore, it is, see, I naught max for 0 to t by 2 and it is a negative I naught max for remaining t. So therefore, this is the thing that we are going to get for this highly inductive load. So this is the further thing we are going to get for highly inductive load. This is the thing that we are going to get. So we can say that S1 S2 are going to conduct, because in this range output voltage is positive and the output current is also positive. It indicates that if both are positive, it simply indicates that both S1 and S2 are on. Whereas in the remaining range, simply both the output voltage and the output current are negative. If both are negative, means simply we can say S3 S4 are on. So this is the diagram we are going to get the output current whenever the load is highly inductive in nature. Special case of this RL. So now we are going to study about the RLC load. So this is the RLC load we are going to keep, and then we are going to understand the circuit. So this is a single phase full bridge voltage source inverter. So we are going to keep the RLC load. This is a plus or minus VDC by 2, plus or minus VDC by 2, S1, S2, S3 and S4. Diode D1 and diode D2, D3 and D4. This is the same as the previous circuit. Only thing is we are going to keep the extra load, which is the RLC load, and the output voltage is plus or minus V naught of t, and the output current is I naught of t. As I've already told you, irrespective of the load, the output voltage will be always here from 0 to t by 2. The output voltage is plus VDC, whereas from t by 2 to t, the output voltage is minus VDC. So this is the nature of the output voltage we are going to get. So therefore now we have to find what is the value of the output current. So now we have to find what is the value of the output current. As I have already told you, whenever you are going to give a DC voltage to a RLC load, the current will be a sinusoidal waveform. So we are going to get a sinusoidal waveform. So this is a sinusoidal waveform we are going to get. If XL is greater than XC, means simply we can say that it is highly inductive circuit. So in a highly inductive circuit, the current is going to lag the supply voltage by small amount of angle phi 1. So if this is phi 1, it will be pi plus phi 1, and here it will be 2 pi. Again next zero will be 2 pi plus pi 1. So this is the graph that we are going to get, because it is called as overdamped system. So now you can see clearly when 0 to phi 1. So when 0 to phi 1, the voltage is positive and the current is negative. From 0 to pi 1, we can simply say that the voltage is positive and the current is negative. So voltage is positive and the current is negative means simply we can say that D1, D2 are conducting. Whereas from pi 1 to pi, the voltage is positive and the current is also positive. When both are positive means S1, S2 are conducting. Similarly, from pi to pi plus phi 1, voltage is negative and the current is positive. It indicates that D3, D4 are conducting. Similarly, pi plus phi 1 to 2 pi, voltage is negative and the current is also negative. If both are negative, again means S3, S4 are conducting. So this is a thing that I have already told you in the previous one only. So based on this, we are going to draw the yes, and which period the switches are going to connect, we are going to draw this. So this is the minus I naught max and this is the plus I naught max, means the maximum value of the output current. Similarly, for underdamped system, means whenever the XL is less than XC or simply X is greater than XL, so we can say that the capacitor reactance is higher than the inductor reactance. So therefore the overall circuit is going to act like a capacitor circuit. Whenever the circuit is acting like a capacitor circuit, means the current is going to lead the supply voltage by small amount of angle. Let me assume phi 1. So if this is phi 1, this will be pi plus phi 1 and this will be 2 pi minus phi 1. So like a pure sinusoidal we are going to get. So this is underdamped and this is overdamped. So easy way to remember is like OU University. The first one is overdamped and this is the underdamped. So you can see clearly here also the maximum value of the output current is plus I naught max and minus I naught max. So from 0 to pi minus phi 1. So from 0 to pi minus phi 1, the voltage is positive, the output voltage is positive and also the output current is also positive. If both are positive means S1, S2 are connecting. Similarly, from pi minus phi 1 to pi, from pi minus phi 1 to pi, you can see the output voltage is positive and also the output current is negative. Whenever the output voltage is positive and the output current is negative, D1, D2 are conducting. Similarly, from pi to 2 pi minus phi 1, the output voltage is negative and the output current is also negative. When both are negative means S3, S4 are conducting. Whereas from 2 pi minus phi 1 to 2 pi, the output voltage is negative and the output current is positive. If that is the case, then D3, D4 is conducting. This is the thing that I have already told you in the previous ones only. So with the help of these things, we have drawn the output voltage and output current for two different conditions. One is overdamped and one underdamped. And then we have also determined what is the range of the diodes and transistors are going to be conduct. See here, whenever S2, S1 are, whenever the S1, S2 are going to connect from 0 to pi minus 5. After that, whenever the D1, D2 are conducting, then we can say that at the moment D1, D2 are conducting, S1, S2 are going to get turned off by default because of the negative reverse bias voltage. So because of this, we can say that you don't need any forced commutation to turn off the thyristors in the underdamped system. Only we need the forced commutation, or we can say forced commutation in order to turn off the thyristors in the overdamped. Only in this case we need the forced commutation thyristors to turn off the thyristors. Whereas here we don't need any forced commutations because by natural way only it is going to turn off the thyristors. Whenever the D1, D2 are on, it is going to turn off S1, S2 automatically. Similarly, whenever the D3, D4 are on, they automatically is going to turn off the S3, S4. This is the one of the important things that you need to understand. So now we are going to do some more analysis of the circuit. I have already told you from the graph, you can see clearly, irrespective whether it is overdamped or it is underdamped, you can see clearly the conduction angle of each diode is equal to phi 1. So the conduction angle of each diode is equal to phi 1, whereas the conduction angle of each thyristor is equal to pi minus phi 1. So whereas conduction angle of each thyristor is equal to pi minus phi 1. Self-commutation is possible for thyristors only in the leading load condition. This also I have already told you. Self-commutation means natural commutation is only possible in the underdamped system. It is possible only in the underdamped system of the leading load condition. So in this condition, if you want to find what is circuit turn-off time is equal to, because diodes are going to connect only for phi 1 range. For this range only, the thyristors are going to face a reverse voltage. So therefore, phi 1 by omega naught is the circuit turn-off time for these thyristors in the underdamped system, because only in this case self-commutation is possible. So now I want to write what is the Fourier series expansion for the output voltage and also the output current. Because I have already told you, as the output voltage is a periodic signal, so we can write the Fourier series V naught of t is equal to sigma n is equal to 1 3 pi up to infinity for the peak value which is VDC by n pi sin n omega naught. So if you want to find what is the output current, so output current is equal to sigma L is equal to 135 up to infinity 4 VDC by n pi mod of Zn sine of n omega naught t minus phi n. So mod Zn is equal to under root over r square plus n omega naught L minus 1 by n omega naught c whole square. Whereas phi n is equal to tan inverse of n omega naught L minus 1 by n omega naught c by r. So this is the value of the phi n you are going to get. So I want to find what is the maximum value of the fundamental component of the output voltage. So P per n is equal to what we are going to get 4 VDC by pi. Similarly, I want to find what is the maximum value of the fundamental component of the output current. So here substitute n is equal to 1, we are going to get 4 VDC by pi of magnitude of Z1. So 4 VDC by pi of magnitude of Z1 we are going to get. So fundamental displacement factor is equal to cos of the phase angle between the fundamental output voltage and fundamental output current is equal to phi 1. So this is the phi 1 we are going to get. So if you want to figure out what is the diode and switch current waveform. So if you want to find what is the waveform of the diode and also the switch current, as I've already told you, the diodes are conducting only from 0 to pi. So the 0 to pi 1 only diodes are conducting. So whenever, let me take a condition of diode D1. See, diode D1 is conducting only from 0 to phi 1. So simply we can say that here, for 0 to phi 1, the diodes are conducting diode D1. So therefore, by seeing the circuit, we can say that the diode current is negative of the output current. So it will be like this. Actually, it will be negative of the output current. Output current in this fashion. So negative of the output current is, actually the graph will be like in this manner we are going to get. Whereas a thyristor current, see, let me take a switch S1. So for this, switch S1 is conducting only from phi 1 to phi. For which one? For overdamped case. So this graphs I am going to draw only for overdamped case. So phi 1 to pi, the switch S1 is connecting. Whenever the switch S1 is connecting, you can see from the graph, the switch current is equal to the output current. So therefore, whatever the output current in this range, it will be same as the switch current. So therefore, we are going to get same as this one we are going to get. So IT1 is called as the diode 1 current, or means current in the diode 1, whereas IT1 called as the current in the thyristor 1. So if the fundamental component of diode average and RMS value, means I want to find what is the average and RMS value of the fundamental component of the diode. The fundamental component of the diode, I want to find what is the average and the RMS. So average value of the fundamental component of the diode current is equal to 1 by 2 pi integration of 0 to phi 1, because only in this range when diode D1 is connecting and the remaining range diode is not conducting. So whenever the diode is connecting, the diode current is negative of the load current. So therefore, means here also, given the fundamental component also, the fundamental component of diode current is the negative of the fundamental component of the load current. So therefore, you have to go, actually you have to keep your negative value. So minus of I01 max into sine of omega naught t minus phi 1 into d theta. Similarly, if you want to find what is the RMS value, the RMS value of the fundamental component of the diode current is equal to 1 by under root over 1 by 2 pi integration of 0 to phi 1 minus of I01 max into sine of omega t minus phi 1 whole square into d theta. So you are going to get like this. Similarly, the fundamental component of the thyristor average and the RMS value. So you want to find what is the value of the average and the RMS value of the fundamental component of the thyristor current. So the average value of the fundamental component of thyristor current is equal to 1 by 2 pi integration of, because for the overdamped system, the switch S1 is connecting only from phi 1 to pi. So phi 1 to pi. Here, whenever it is equal, the switch current is equal to current in the load. Similarly, you can say simply, we can also say that fundamental component of the switch current is also equal to fundamental component of the source current, the load current. So the fundamental component of the switch current is equal to fundamental component of the load current. So therefore, I01 max into sine of omega naught t minus phi 1 into d theta. Similarly, the RMS value of the fundamental component of thyristor current is equal to under root over 1 by 2 pi integration of phi 1 to phi. Here also same thing. So I01 max into sine of omega naught t minus phi 1 whole square into d theta. So now we are going to discuss about the introduction to PWM. So we are going to study some of the important topics of the PWM, pulse width modulation. The first thing we are going to study about the single pulse width modulation, and then we are going to study the multiple pulse width modulation, and then we are going to study the Fourier series of unequal pulse width modulation, and then sinusoidal pulse width modulation. Sinusoidal pulse width modulation is divided into two types: bipolar pulse width modulation and unipolar pulse width modulation. So in the pulse width modulation, we are going to study all these things in a very detailed manner. Single pulse width modulation, multiple pulse width modulation, Fourier series of unequal pulse width modulation. In the sinusoidal pulse width modulation, we are going to study the bipolar pulse width modulation and also the unipolar pulse width modulation. So now we are going to study general output waveforms of single phase full bridge inverter by using different PWM. So general output waveforms of single phase full bridge inverter by using different pulse width modulation. So generally what I am trying to say is, by using the different pulse width modulation techniques, how the output voltage or the output voltage of single phase full bridge inverter we are going to get. So by using different pulse width modulation, so what is the output voltage? What is the output voltage that we are going to get for single phase full bridge inverter? See, in the previous we have already studied, irrespective of the load, always the voltage source inverter, the output voltage is always constant. But now we are going to modify it, means we are going to modify in terms of pulses. So if you do that one, we are going to change the RMS value and also the average value also we are trying to change with the help of this pulse width modulation. So this is the output voltage we are going to get for single pulse width modulation. So if you use the single pulse width modulation technique, then the output of the single phase full bridge inverter we are going to get in this format. So there is a pulse width of 2D. So pulse width of 2D, the peak value of VDC, and similarly here it is also minus VDC. So with the pulse width of 2D here also. So we can see from 0 to pi there is only one pulse. So there is only one pulse. That is the reason we call it as a single pulse width modulation. So in half of the cycle, if there is only one pulse, then we are going to say it is a single pulse width modulation. So this is the nature of the output we are going to get if you use the single pulse width modulation for the single phase full bridge inverter. So the pulse width is 2D. So now if you are going to use multiple pulse width modulation, means if you get more than one signal, if you get more than one pulse in half of the time period, in half of the cycle, if you get more than one pulse, then we call this as the multiple pulse width modulation. Means in half of the cycle, if you get more than one pulse, it is called as the multiple pulse width modulation. So if you use the multiple pulse width modulation, then the output of the single phase full bridge inverter we are going to get in this format. Here we are going to get 3 pulses in half of the cycle. So therefore the total pulse width is 2D. So as there are 3 pulses, means 2D by 3. So 2D by 3, 2D by 3 and 2D by 3. So 2D by 3 is the pulse width of each pulse. So if you want overall, if you have to add all these things to get the total pulse width as 2D. So the pulse width of each pulse is 2D by 3 here, because there are 3 pulses. So this is the nature of output we are going to get if you use the multiple pulse width modulation to generate the output voltage of single phase full bridge inverter. So now if you use unequal pulse width modulation, technique, then the nature of the output, that we are going to get in the single phase full bridge inverter is in this format. You are going to get like this. So you can see it has a very high pulse width, again low pulse width, again high pulse width, again low pulse width, again low pulse width and high pulse width. So you can see clearly. Here these are complex conjugate. So these are the complex conjugate in nature, and also the pulse width are different. This pulse width is not equal to this pulse width. So therefore unequal pulse width is going to present. So if unequal pulse width is going to present in a given time period, so in a given half of the cycle, if the pulses are of different nature, then we call this as the unequal pulse width modulation. So therefore this is called as the unequal pulse width modulation. So by using the unequal pulse width modulation, we are going to get a pulses of different width, different length or different width we are going to get. That is the nature of this unequal pulse width modulation, and this is the output voltage of the single phase full bridge inverter by using this unequal pulse width modulation. So now if you use the sinusoidal unipolar PWM technique, technique, then the nature of the output voltage we are going to get at the output of single phase full bridge inverter is, this is the format we are going to get in terms of sine wave. So simply the pulse width is going to increase slightly. It's going to increase slightly up to pi by 2, and then it is going to decrease. And again it is going to increase, and again it is going to get decrease. So this is the nature of the pulse width, or we can say this is the nature of the output voltage we are going to get if we use the sinusoidal unipolar PWM. So in a 0 to pi, each and everything is going to have only positive value. So in half of the cycle, you can say clearly each and everything is going to have positive value. So that is the reason it is called as the unipolar. So unipolar, and it is also in the shape of a sine wave. So therefore, sinusoidal unipolar PWM technique. Suppose if we use the sinusoidal bipolar PWM technique, then the output voltage we are going to get at the output of a single phase full bridge inverter is in this format: plus VDC minus VDC. So it is going to increase slightly, again it is going to decrease, again it is going to increase, again it is going to decrease. So you can see from 0 to pi in half of the cycle, you can see plus VDC and also minus VDC. So two things are possible. So therefore this is called as a sinusoidal bipolar PWM. Sinusoidal bipolar PWM, because in a given half cycle you are going to get positive VDC and also negative VDC. So because of that we can say this is sinusoidal bipolar PWM. So now we are going to discuss the generation of multiple pulse width in the output in a single phase full bridge inverter. So in a single phase fully bridge inverter, we are going to generate multiple pulse width in the output. So here we are going to generate the multiple pulse width in the output in a single phase full bridge inverter. We are going to study in a detailed manner. So before we study regarding the graphs, we must study about the circuit. See here, this is a comparative circuit. So basically it is the op-amp, open loop op-amp. So we are going to give two signals to input of this comparator. One is a reference signal and other is a carrier signal. And then we are going to generate the pulse. So based on comparison of the reference signal and the carrier signal, we are going to generate this pulse. So this pulse is used to trigger the thyristors. So we are going to use this pulse to trigger the thyristors in such a way, then we are going to get the output. So if Vc of t is greater than Vr of t, if the carrier signal is greater than the reference signal in the positive half cycle, then trigger S1, S2, then V0 is equal to VDC. So whenever the carrier signal is always greater than the reference signal, then only in the positive half cycle, then trigger the S1 and S2 switches. So therefore if you trigger the S1 and S2, so by using the circuit diagram of the single phase fully bridge inverter, so output voltage is equal to plus VDC. In the if minus VCT is greater than minus VRT in the negative half cycle, then trigger S3, S4, then V0 is equal to minus VDC. So you can see clearly here, if minus VCT is greater than minus VRT in the negative half cycle, then trigger S3, S4. So therefore output voltage is equal to minus VDC. So this is the way that we are going to trigger the thyristors. In such a way we can get the output as plus VDC or the output as minus VDC. So now this is a carrier signal. This is basically a carrier signal, and this is called as a reference signal. So this is a reference signal. So you can see clearly this is called as a carrier signal, and this is a carrier signal, and this is the reference signal. So now the reference signal time period is TR, whereas the carrier signal time period is TC. So TC is the carrier signal time period, and TR is the reference signal time period. So now you can see clearly one important point. You can see one clearly important point here. In this period, Vc of t is greater than Vr of t. Only in this period, Vc of t is greater than Vr of t. So in the positive half cycle, whenever the Vc of t is greater than Vr of t, then we are going to trigger S1, S2. So therefore, the output voltage is equal to plus VDC. Here also, again in this range also, again in this range also. So therefore, in the positive half cycle, these ranges where the carrier signal is greater than the reference signal. So therefore, we are going to trigger the T1, T2. So therefore, the output voltage is equal to plus VDC. So this is the plus VDC, and plus VDC. So you can see clearly in half of the time period of the reference signal, there are three pulses we have generated. So we have three pulses we have generated. I already told you overall pulse width is equal to 2D. So therefore, if you want pulse width of each and every signal, which is 2D by 3, because there are three pulses, 2D by 3. Similarly here, minus Vc of t is greater than minus Vr of t. So in the negative half cycle, so therefore here also we are going to trigger the S3 S4. So therefore the output voltage is equal to minus VDC. So in this range the output voltage is equal to minus VDC. Here also the output voltage is equal to minus VDC. Here also the output voltage is equal to minus VDC. So this is the way that you are going to get here. So this is the triggering method by which we are going to get the multiple pulse in a given half cycle. So you always, one important point is here, the frequency of the output signal is equal to the frequency of the reference signal. Whereas if you increase the frequency of the carrier signal, the number of pulses in a given half cycle are going to get increase in the output signal. So if you increase the frequency of the carrier signal, the number of pulses in a given half cycle is going to get increase. That is the meaning of this one. As the output signal frequency is always equal to say frequency of this reference signal, where n is equal to number of output pulses in half cycle. So n is called as the number of output pulses in half cycle. So in the output voltage in a given half cycle, the number of pulses present are called as the n. So in a given output signal, in a given half period, the number of pulses present are called as the n. So n is the number of output pulses in half cycle. It is also called as the number of carrier pulses in half cycle. It is also equal to number of carrier pulses in half cycle. So n is also equal to number of carrier pulses in half cycle. Means number of carrier pulses in half cycle is equal to number of pulses we are going to get in the output of this V0 in half cycle. So therefore n is called as the number of output pulses in half cycle or the number of carrier pulses in half cycle. Here 2D is called as the total pulse width output in half cycle. So in a given half cycle, the total pulse width is called as a 2D. So 2D is called as the total pulse width of output in half cycle. Whereas 2D by n. So 2D by n is called as the each pulse width of output in half cycle is equal to W. So it is also called as W. So W is equal to 2D by n. So 2D by n is called as the each pulse width of output in half cycle is also equal to W. So therefore the pulse width of simply we can say that the pulse width of each pulse in a given half cycle in the output voltage is equal to 2D by n. So 2D by n is also equal to W. So W is the each pulse width of output in half cycle. So simply we can say that the number of output pulses in half cycle is n. It is also equal to number of carrier pulses in half cycle. Here 2D is the total pulse width of output in half cycle, and 2D by n is also equal to W. It is called as the each pulse width of output in half cycle. So 2D by n is equal to simply each pulse width of output in half cycle is equal to W. So simply I can say that n is called as the number of output pulses in half cycle, or simply the number of carrier pulses in half cycle. So 2D is the total pulse width of output in half cycle. So therefore 2D by n is called as the each pulse width of output in half cycle is equal to W. Simply I can say that n is called as the number of pulses we are going to get in the output in half cycle, or simply we can say that the number of carrier pulses in the half cycle. Or 2D is called as the total pulse width of the output signal in a given half cycle. That is 2D by n is called as the each pulse width of output in half cycle is equal to W. So now we are going to do some more analysis. So from the diagram we can see clearly, that 3 into Tc. So 3 into Tc is equal to Tr by 2. So you can see clearly 3 into Tc is equal to Tr by 2. So 3 into Tc means the overall width of this we are going to get is equal to half of the time period of the reference signal. So 3 into Tc is equal to, so 3 into Tc is equal to Tr by 2. So 3 into Tc is equal to Tr by 2. So therefore 3 is equal to, see if you do simplification we are going to get 3 is equal to Fc by 2Fr. So therefore simply n is equal to Fc by 2Fr means here we can say that n is equal to Fc by 2Fr simply indicates that this is called as the Fc by 2Fr. Fc is the frequency of the carrier signal and Fr is the frequency of the reference signal. Always Fc is greater than Fr. So therefore n is equal to Fc by 2Fr. So n indicates the number of pulses we are going to generate in the output. In the half cycle we are going to get is equal to Fc by 2Fr. So let me take a value which is m is equal to Vr by Vc. So m is called as a modulation index. It is a ratio of the peak value of the reference signal by peak value of the carrier signal. So always VR is always less than VC. So always VR is always less than VC. It's a condition. So always VR is less than VC. Then only we are going to generate the pulses. Then only we are going to generate the pulses. Otherwise what is going to happen? If VR is less than VC only, then only we are going to generate the pulses. Otherwise we are not going to generate the pulses in the output voltage. That is the reason always VR is always less than VC, then only we can generate the pulses in the output. Otherwise, we are not going to get anything. Suppose if VR is greater than VC means simply we can say at no condition it will be VC is greater than VT. So therefore, we are not going to get any output pulse. So always VR is always less than VC, then only we are going to generate the output pulses. So therefore, it indicates that the MS can lie only from 0 to 1. But M is called as a modulation index. So VR of t is called as a reference signal. So VR of t is called as a reference signal. So VR of t is called as a reference signal. See here we have used the reference signal as square waveform. Whereas a VC of t is called as a carrier signal, and here we have used the triangular waveform. So reference signal we have used as the square waveform, whereas a carrier signal we have used as a triangular waveform. So n is equal to fc by 2fr. It's a very important formula. So now we are going to some more do the specific analysis of this one. We are going to see clearly. So now see, this is called as a carrier signal. So this is called as a carrier signal, and this is called as a reference signal. So this is the carrier signal and this is the reference signal. So let me take few points: A, B, C, D, E. This is M and this is O. See, this is the base point. This is the base point. So this is the base point means this is the VR and this is VC. So overall this side is VC minus VR. So therefore this is the base point. So therefore this is VR means this is overall VC. So therefore this will be VC minus VR. So now I have already told you only in this range VC of t is greater than VR of t. So therefore we are going to get a pulse width in this range. So the W is called as a pulse width. So this is the pulse width we are going to generate. So this is the pulse width we are going to generate in the output voltage. And also here, so let me assume if there are n triangular pulses in a given half of the time period of the reference signal. So therefore, if there are, simply we can say that if there are n pulses of carrier signal in a given half period, so each pulse width will be equal to pi by n. So pi by n. So you can see clearly it's 0 to pi. As there are n pulses, so each pulse width will be pi by n. So therefore pi by n. So therefore, but here there are 3 pulses. So each pulse width will be pi by 3. So this is from here to here. This is pi by 3. But if you want for general case, it is pi by n. So pi by n. Because we are going to draw it with respect to theta. This as a theta. So triangle ADE and triangle ABC are similar triangles. So triangle ADE and triangle ABC are the similar triangles. So we can do the corresponding ratio equal, which is OA by AM is equal to DE by BC. So OA by AM is equal to DE by BC. Now these two triangles are equal, similar, so we can go for this ratio. This one by this one, this one by this one. So OA is equal to VC minus VR, whereas AM is called as VC is equal to, whereas D is called as the W, whereas this is called as the pi by n. So if you do the simplification, finally we are going to get W is equal to pi by n into 1 minus n, where m is the VR by VC. So you are going to get in this format. So general pulse width of any signal is equal to, the pulse width of any signal is equal to pi by n into 1 minus n, where m is the VR by VC. So therefore finally the pulse width is equal to 2d by n into pi by n into 1 minus n. M is the ratio of VR by VC. So we can say that simply W is called as the pulse width of each pulse in half of the time period, in half of the cycle is equal to 2d by capital N is equal to pi by capital N into 1 minus n. M is the ratio of the VR by VC. Always VR is always less than VC. And also I have already told you the capital N is equal to FC by 2FR. So N means the number of pulses we are going to get in the output signal in half of the time period, and it is also equal to number of pulses of the carrier signal in half of the cycle. So now we are going to discuss about the multiple pulse width modulation. Multiple pulse width modulation means, see, this is the output we are going to get in a multiple pulse width modulation. Simply indicates that multiple pulse width modulation means in a given half cycle, if you get more than one pulse, it is called as the multiple pulse width modulation. So let me assume this is the output voltage we are going to get, which is of 3 pulses. So overall pulse width is nothing but 2D. So pulse width of each signal is 2D by capital N. So 2D by N is the pulse width of the each and every signal. So this is basically a half wave signal plus odd. So therefore this is half wave symmetry plus odd signal. So you can see clearly this is a odd signal, and also it is a half wave symmetry. Means if you shift it by pi, if you shift the signal by pi, and if you do the reciprocal, you are going to get the again. So listen carefully. It is odd signal. And also if you shift the signal, if you shift this V0 by some pi, and if you do the reverse of it, you are going to get the original signal. So this is called as half wave symmetry. So listen carefully. As it is an odd signal, and also if you shift the signal by pi, and if you do the reverse, again you are going to get the same signal. That is called as the half wave symmetry. So this is half wave symmetry, and also it is an odd signal. So here N is called as the number of pulses in the half cycle. So in the output voltage you can see the number of pulses in the half cycle is equal to 3. So therefore capital N is equal to 3. So N indicates the number of pulses in the half cycle in the output signal, or the number of carrier pulses in a given half of the time period. So it is equal to 3. Whereas W is called as the pulse width of each pulse in the output in a given half of the cycle. So each pulse width in half cycle is equal to 2D by capital N, but here N is equal to 3. So therefore 2D by 3. So the distance, each and every distance is equal. So this distance is equal in a given half cycle. So therefore this is the equal distance, this is also equal distance, and this is also equal distance, and this is also equal distance. So each space width in half cycle is equal to, So here, see, I want to find what is this length, each space width in the given half cycle. So if this total is gamma, let me assume if the total is length is gamma. So gamma minus 2dn by 2. So you are going to get d by n. So gamma minus d by n. So this is the thing that you are going to get. Therefore this space width is equal to gamma minus d by n. And gamma is from this one to middle one. So gamma minus d by n is the space width in each half cycle. It is going to have equal length. So now we are going to analyze this circuit. See, I want the overall pi is equal to, see, this length plus this length is equal to 2d by n into 2d by 3 into 3 is nothing but 2d plus again 1, 2, 3, 4. There are 4 things. So 4 into this length, which is 4 into gamma minus d by n plus 2db is equal to pi. So 4 times of this length plus overall pulse width is equal to pi. So now we are going to use some general format. This is for 3 types of signals, for 3 pulses in a given half cycle. But generally it will be n plus 1 into gamma minus d by n plus 2d is equal to pi. So here, if there are n pulses, we are going to get n plus 1 number of times of space width we are going to get. So n plus 1 into gamma minus d by n plus 2d is equal to pi. So if we do simplification, finally we are going to get gamma is equal to pi minus 2d by n plus 1 plus d by n. So simply I can say that here n plus 1 into gamma minus d by n plus 1 into gamma minus d by n plus 2d is equal to pi. So if you solve this one, gamma is equal to pi minus 2d by n plus 1 plus d by n. So gamma is equal to pi minus 2d by n plus 1 plus d by n. So this is the gamma that you are going to get with respect to origin. This is in terms of angle theta, in terms of radians. So half wave symmetry I have already told you. Half wave symmetry means f of theta is equal to minus of f of theta plus phi. Means if you delay the signal by pi, and if you do the reverse means negative, then you are going to get the original signal, whether you make it delay or advance, everything is same. So if f of theta is equal to minus of f of pi plus theta, simply I can say that whether you delay or whether you do advance by pi, And if you do the negative of that, by using that, if you get the same signal, that is called as half-wave symmetry. Odd signal means f of minus theta is equal to minus of f of theta. Then we say that signal is said to be an odd signal. So f of theta, f of minus theta is equal to minus of f of theta. Then we are going to get this is called as odd signal. So this signal is going to satisfy these two properties, off-wave symmetry and also the odd signal. So output voltage is an off-wave symmetry and also an odd signal then. So therefore, I already told you the output voltage here, it is also off-wave symmetry and also it is an odd signal. So then what is going to happen? Then if it is signal is an odd signal, if it is an odd signal, I have already told you if it is odd signal means V0 is equal to 0 and also AM is equal to 0. Whereas Bn is not equal to 0 only for odd harmonics, only for odd harmonics. See, only odd harmonics are going to present. Only the odd harmonics of sine terms are going to present. So whenever a signal is off wave symmetry and also odd signal, then we can say A0 is equal to 0 and An is also equal to 0, and Bn is not equal to 0 for only odd terms. Only for odd harmonics are going to present. Only odd harmonics are going to present. So V0 of t, if you want to expand terms of Fourier series, is equal to sigma n is equal to 135 up to infinity Bn sin n omega naught t. So if you want to find what is the value of Bn with the help of Fourier series, so we can get easily the Fourier series expansion of this one is very simple, which is here 2 by 2 pi integration of, so 2 by 2 pi integration of, so 2 by 2 pi integration of gamma minus d by n to gamma plus d by n. So here in this range we are going to get the signal. The signal is called as a plus VDC. So plus VDC into sin n omega t into d omega t, or simply we can say sin n theta into d theta into, we are doing for only one signal, but we want for whole series into n. Into n means we are going to go up to half cycle, but it is, if we want full cycle, so we need to go for 2. So therefore, you are going to do this integration for the total thing that you are going to do for 2 pi. So therefore, Bn is equal to 2 by 2 pi integration of gamma minus d by n to gamma plus d by n, which is VDC into sin n theta into d theta into n into 2. Because the general format of Bn is equal to 2 by the total time interval into integration of over the total time period into f of t into sin n theta into d theta. That is the actual way. So here Bn is equal to 2 by 2 pi integration of gamma minus d by n to gamma plus d by n. In this range, the output signal is equal to VDC. So VDC into sin n theta into d theta into, we have to do for whole range of 2 pi. So therefore into n means we are doing for only half cycle. Again it is a symmetry. So therefore into 2 for overall things, full cycle. So if you solve this one, we are going to get finally Bn is equal to n into 4 VDC by n pi sin n gamma into sin n d by n. So Bn is equal to n into 4 VDC by n pi into sin n gamma into sin n d by n. So this is the value of Bn we are going to get. So if you substitute in this output voltage, finally the expression that you are going to get is, so V0 of t is equal to n into sigma small n is equal to 135 up to infinity 4 into VDC by n pi sin n gamma into sin n d by capital N into sin n omega naught t. So this is the expression of the output voltage that you are going to get general format for any multiple pulse signal. So n means the number of pulses in the output voltage in a given half cycle. 4 into VDC by n pi sin n gamma. Gamma is nothing but, simply we can say that from origin to that middle point. So therefore gamma. So sin n d by capital N. So d by capital N into sin n omega t. So this is the expression of the output voltage of multiple pulse width. So you have to remember, whenever a signal is satisfying, it is an off-wave symmetry and also it is an odd signal, then A0 is equal to 0 and Am is equal to 0. Only odd harmonics are going to present in Bn. So only sine terms are going to present, which are purely odd. So therefore V0 of t is equal to a capital into sigma small n is equal to 135 up to infinity 4 VDC by n pi sin n gamma into sin n d by n into sin n omega t. So V0 of t is equal to capital N into sigma small n is equal to 135 up to infinity 4 VDC by n pi sin small n gamma into sin small n d by capital N into sin small n omega t. So this is the output expression we are going to get. So V naught of t is equal to capital N sigma small n is equal to 135 up to infinity 4 VDC by n pi sin small n gamma into sin small n d by capital N into sin small n omega t. So this is the output expression that you are going to get. So V naught of t is equal to capital N into sigma n is equal to 135 up to infinity 4 VDC by n pi into sin of n gamma into sin of n d by capital N into sin of n omega t. So we are going to write for general expression. So we know the general expression. So now we are going to write for single pulse width. So for single pulse width in a given half cycle, there is only one pulse. So for single pulse width means in a given half cycle, there is only one pulse. So one pulse in the half cycle means n capital N is equal to 1. So if you substitute gamma is equal to pi minus 2d by capital N plus 1 plus d by capital N. So pi minus 2d by capital N plus 1 plus d by capital N. If you substitute capital N is equal to 1 and if you solve this one, we are going to get pi by 2. So now the general expression is equal to V naught of t is equal to capital N into sigma n is equal to 135 to infinity 4 VDC by n pi into sin n gamma into sin n d by capital N into sin n omega t. So if you substitute capital N is equal to 1 and gamma is equal to pi by 2, then we are going to get finally sigma n is equal to 135 up to infinity 4 VDC by n pi into sin n pi by 2 into sin n d into sin n omega t. So this is the expression that you are going to get for when the only single pulse we are going to present in the output. This is a single pulse. So now we are going to do the analysis of this voltage waveform. We are going to do some more analysis. So V naught RMS is equal to, so V naught RMS is equal to VDC into under root over the pulse width is in a given half cycle, the pulse width is 2D, so 2D by pi. So therefore V naught RMS is equal to VDC into under root over 2D by pi. Similarly, if you want to find what is the peak value of the fundamental output voltage, the peak value of the fundamental output voltage is substitute small n is equal to 1, you are going to get 4 VDC by pi into sin pi by 2 into sin d. Sin pi by 2 is 1, so therefore 4 VDC by pi into sin d is the peak value of the fundamental output voltage. If you want the RMS value of the fundamental output voltage, so peak value by root 2, so you are going to get this expression. Suppose to remove nth harmonic component, so if you want to remove the nth harmonic component, which is specifically odd only you can remove the odd things only, because even things are default 0, so only odd things are going to present. And if you want to remove a specific of odd term, how to remove it? Because the sin nd is equal to 0 by choosing a proper pulse width. So sin nd is equal to 0. So if you substitute nd is equal to k into pi, so k can be from 1, 2, 3 up to infinity. So therefore, but I want 2d, so 2d is equal to 2 pi k by n. So this is called as the overall pulse width. So this is the pulse width of given one pulse. You can say 2d is called as a pulse width of, this is the pulse width because capital N is equal to 1, only one pulse is going to present in half cycle. That pulse width is equal to 2d is equal to 2 pi k by n. So always k can lie from 1 to up to infinity, but n cannot be 1 because we cannot remove the fundamental component, so n cannot be 1. And also 2d can only lie from 0 to 180 degree because only half cycle, because the pulse is going present in only half cycle, so 2d can lie from only 0 to 180, it cannot be more than this. So 2d is equal to 2 pi k by n. So therefore n can lie from 1 to up to infinity, whereas 2d can lie from only 0 to 180 degree. Suppose let 2d is equal to 72 degree, then what is going to happen? If 2d is equal to 72 degree, then what is going to happen is the V01 peak value. I already told you the peak value of the fundamental output voltage is 4 VDC by pi into sin d. So if you substitute in the expression, we are going to get 0.74 VDC. So V01 peak value is equal to 0.74 VDC. So G is called as a distortion factor ratio of the RMS value of the fundamental output voltage by RMS value of the overall output voltage. So we know the ratio, the RMS value of the fundamental output voltage and also the RMS value of the overall output voltage. You can do the division to get the value of G, and also PhD is equal to under root over 1 by G whole square minus 1. So we can get the expression of each and everything. We are going to get in a very easier format. So for two pulse width modulation means in a given output voltage of single phase full bridge inverter, we are going to get 2 pulses in the output voltage like given after the cycle. So what is the expression of the voltage and each and everything, we are going to do the analysis. So 2 pulses in the half cycle. So capital N is equal to 2, whereas gamma is equal to pi minus 2d by capital N plus 1 plus d by capital N. So if we substitute capital N is equal to, we are going to get pi by 3 minus d by 6. I have already told you the general expression V naught of t is equal to capital into sigma n is equal to 135 up to infinity 4 VDC by n pi into small n gamma into sin n gamma into sin n d by capital N into sin n omega t. So if you substitute capital N is equal to and gamma is equal to pi by 3 minus d by 6, so you are going to get, this is the expression that you are going to get finally, which is V naught of t is equal to sigma n is equal to 135 up to infinity 8 VDC by n pi sin n of pi by 3 minus d by 6 into sin n d by 2 into sin n omega t. So this is the thing that we are going to get. So now we are going to do some more analysis of this circuit of this one waveform. So V naught RMS is equal to VDC into under root over the overall pulse width here, as there are 2 pulses, so each pulse is width of 2d by 2, but overall is 2d, so 2d by pi. So this is the output RMS value we are going to get. And if I want to find what is the peak value of the fundamental output voltage, if you substitute m is equal to 1, we are going to get 8 VDC by pi into sin pi by 3 minus d by 6 into sin d by 2. So if you substitute small n is equal to 1, we are going to get the peak value of the output voltage. Now if you want to find what is the RMS value of the fundamental output voltage, so peak value by root 2, so you are going to get, this is the value we are going to get. So if you want to remove the nth harmonic, component from this output voltage, so simply sin n d by 2 is equal to 0, so therefore n d by 2 is equal to k pi, so therefore d is equal to 2k pi by n. So if you want 2d, so 2d is equal to overall pulse width is equal to, so overall pulse width is equal to 2d is equal to, you can simply say that 4k pi by n, that is the overall pulse width. But if you want to find what is the pulse width of each pulse, because it is a 2d by 2 plus d, so this is the pulse width of each pulse, d is equal to 2k pi by n. So therefore k can range from 1, 2, 3 up to infinity. So we cannot remove the fundamental component, so n is not equal to 1. So therefore 2d, the overall pulse width is 2d, it is going to lie between 0 to 180 degree. So this is the condition that you need to remember. Suppose if I choose a overall pulse width is equal to 2d is equal to 72 degree, and then I want to find what is the value of the peak value of the fundamental output voltage. If I substitute in that expression, I am going to get the peak value of the fundamental output voltage for an overall pulse width of 2d is equal to 72 degree, I am going to get 0.63 VDC. 0.63 VDC I am going to get. So from the single pulse width and the 2 pulse width waveform, we can analyze that here the peak value of the fundamental output voltage of single pulse width modulation is always greater than the peak value of the fundamental output voltage of the 2 pulse width modulation, because for same 2D. So for same 2D, for same pulse width, for same overall pulse width, you can see clearly that the peak value of the fundamental output voltage of the single pulse width waveform is always greater than the peak value of the fundamental output voltage of the 2 pulse width waveform. Means whenever you are going to increase the number of pulses in a given half cycle, definitely you are going to decrease the peak value also. So whenever you are trying to increase the number of pulses in half cycle, you are going to decrease the peak value also, you are going to decrease. So as number of pulses in half cycle increases, lower order harmonic peak value decreases, and higher order harmonic peak value increases, and overall PhD decreases. So we can say that simply, see, as number of pulses in half cycle increases, then the lower order harmonic peak value decreases and higher order harmonic peak value increases, and overall PhD decreases. So PhD is called as the ratio of the RMS value of the harmonic voltage by the RMS value of the overall output voltage. That is the meaning of the PhD. So therefore simply we can say that if you are going to increase the number of pulses in a half cycle, then definitely what is going to happen, if you are trying to increase the number of pulses in a half cycle, then definitely you are going to increase the, see, as you are going to increase the number of pulses in a given half cycle, you are going to decrease the peak value of the lower order harmonics, whereas you are increasing the peak value of the higher order harmonics. So therefore, overall THD is going to get decreased. That is the meaning of this one. So when you are trying to increase the number of pulses in a given half cycle, the lower order harmonic peak value decreases and the higher order peak value goes on increases and the overall THD decreases. So G is called as the distortion factor. It is a ratio of the RMS value of the fundamental output voltage by the RMS value of the overall output voltage. So we know each and everything. So we can get the value of G. So THD is called under root over 1 by G whole square minus 1. So simply I can say that whenever you are going to increase the number of pulses in a given half cycle, then we can simply say that the peak value means the peak value of the lower order harmonic values goes on decreases and the peak value of the higher order harmonic value goes on increases. So therefore the overall THD decreases. So now we are going to study about the Fourier series application in the pulse width modulation. So now we are going to study the Fourier series application in this pulse width modulation. See, f of theta is equal to means any periodic signal we can write in terms of sine and cosine. So here f of theta is equal to a naught plus sigma n is equal to 1. So sigma n is equal to 1 up to infinity a n cos n theta plus b n sin n theta. So f of theta is equal to a naught plus sigma n is equal to 1 to infinity a n cos n theta plus b n sin n theta. So if you want to find what is the Fourier series coefficients, a naught is equal to 1 by 2 pi integration of 0 to 2 pi f of theta into d theta. Whereas a n is equal to 2 by 2 pi integration of 0 to 2 pi f of theta into cos n theta into d theta. Similarly, b n is equal to 2 by 2 pi integration of 0 to 2 pi f of theta into sin n theta into d theta. So a naught we can also call it as the area of f of theta by time period. Similarly, a n is called as the 2 times the area of product of two functions by time period. So 2 times of area of product of two functions by time period. Similarly, Bn is equal to area of product of these two functions by 2 pi into 2. So simply we can say that f of theta is equal to a naught plus sigma n is equal to 1 to infinity a n cos n theta plus b n sin n theta. So a naught is equal to here 1 by 2 pi integration of 0 to 2 pi f of theta into d theta, and a n is equal to 2 by 2 pi integration of 0 to 2 pi f of theta into cos n theta into d theta. Similarly, b n is equal to 2 by 2 pi integration of 0 to 2 pi f of theta into sin n theta into d theta is equal to area under this graph f of theta by 2 pi, or simply we can say area of f of theta by time period is 2 pi. Similarly, 2 times of area under the product of these two functions by time period. Similarly, this is 2 times the area under the product of these two functions by time period. You will also get these coefficients in this format also. So now we are going to see the different forms of functions so that we can easily do the calculation of this Fourier series coefficients. So when a function is even, what is going to happen? So f of theta is equal to f of minus theta. It is symmetry with respect to y-axis. So f of theta is equal to f of minus theta. So here a naught is equal to, so a naught is equal to a function of time is not equal to 0. Whereas a n is also not equal to 0 because f of theta is an even function and cos theta is also even function. So product of two even functions is again even function. So integration cannot be 0, so not equal to 0. Whereas bn is nothing but f of theta into sin n theta. F of theta is an even function and sin is a cos odd function. So the product of two even function and odd function is overall is also odd function. So integration of in any given time period, for in a one time period of odd functions again 0. So therefore a naught is not equal to 0, n is not equal to 0, whereas bn is equal to 0. That is the thing we can easily simplify for a given even function. So either even or odd function. See, if a function is not even function and not odd function, means simply we can say that f of theta is not equal to f of minus theta, and also f of minus theta is not equal to minus of f of theta. So therefore f of theta is not equal to f of minus theta, and f of theta is not equal to minus of f of minus theta. If any function is not satisfying these two properties, then we can say that the function is not an even function and also not an odd function. So therefore, if this is the case, then a naught is not equal to 0, a n is not equal to 0, and b n is not equal to 0. Means all the Fourier series coefficients are going to get present. So a function is said to be odd function if it is antisymmetric with respect to y-axis. So f of minus theta is equal to minus of f of theta. That is the case we can say this function is said to be an odd function. So f of minus theta is equal to minus of f of theta, or simply f of theta is equal to minus of f of minus theta. Then we can say this function is said to be an odd function with respect to y-axis. So for odd function, definitely a0 is equal to 0 because the function itself odd function. So integration of function in a given time period is equal to 0, and an is a product of two f of theta and cos theta. So f of theta is odd and cos is even. The product of odd and even is again odd. So therefore you are going to get 0. Whereas bn is product of f of theta and sin theta. So f of theta is an odd function and sin theta is also odd function. The product of two odd functions is even. So therefore it cannot be equal to 0. So therefore simply we can say that in an odd function only sine terms are going to present, whereas in even function only cos terms are going to present with a DC signal. So listen carefully. If the function is even function, DC signal and the cos terms are going to present, whereas if the function is a odd function, then only sine terms are going to present. If the function is even function, cos terms and DC signal is going to present. But if a function is odd function, we can say simply that only sine terms are going to present. So now we'll discuss odd function and off wave symmetry. So if any function satisfying these two properties, the function is odd function and also off wave symmetry, then what is the things that we are going to get in the Fourier series coefficients we are going to figure out. Odd function means I have already told you f of minus theta is equal to minus of f of theta, or f of theta is equal to minus of f of minus theta. If any function satisfying this property, then we can say it is said to be an odd function. Similarly, off wave symmetry. Off wave symmetry means f of theta is equal to minus of f of pi plus theta. So f of theta is equal to minus of f of pi plus theta or pi minus theta. So therefore means if you go for lagging or delay or lagging or advanced by pi for a given function, and if you do the negative of that, if it is equal to original function, then we can say it is said to be off wave symmetry. So f of theta is equal to minus of f of pi plus or minus theta. Then we can say that this function is said to be satisfying the property which is called as the off wave symmetry. So if any function satisfying these two properties, odd function and also off wave symmetry. So odd function means I have already told you a0 is equal to 0, an is equal to 0, whereas bn is not equal to 0. That is the case for odd function. If it is off wave symmetry means again the even harmonics are going to get absent, only odd harmonics are going to present. So it is not equal to 0 for only odd harmonics, which are 1, 3, 5 and up to infinity. Only odd parts are going to present but not the even parts. So therefore finally bn is equal to 2 by 2 pi integration of 0 to 2 pi f of theta into sin n theta into d theta. As f of theta is an odd function and sin is odd, so odd into odd is again even. So this is an even function, so you can split into two parts. So 0 to pi, so as the symmetry from 0 to 2 pi is that whatever the thing from 0 to pi again is going to present from pi to 2 pi, so therefore into 2. So this is the easy way to do the simplification. Because it is a symmetric, because it's an even function, so therefore we are going to split into two parts, 0 to pi and pi to 2 pi. So pi to 2 pi is again equal to 0 to pi. So no need to do, so into 2 we are going to get this one. So now if any function satisfying the odd function and also quarter wave symmetry, then what is the things we are going to get from the Fourier series coefficients we are going to see. See, if any function satisfying the odd property and also quarter wave symmetry means f of theta is equal to minus of f of minus theta, then we can say that function is said to be an odd function. See, quarter wave symmetry means very simple. Quarter wave symmetry means f of 90 plus theta is equal to f of 90 minus theta. F of 90 plus theta is equal to f of 90 minus theta, and similarly f of 270 plus theta is equal to f of 270 minus theta. If any function satisfying this property, which is f of 90 plus theta is equal to f of 90 minus theta, and f of 270 plus theta is equal to f of 270 minus theta. If any function satisfying this property, then we can say it is said to be quarter wave symmetry. Half wave symmetry means, I have already told you, half wave symmetry means f of theta is equal to minus of f of pi plus or minus theta. Whereas quarter wave symmetry means f of 90 plus theta is equal to f of 90 minus theta, and f of 270 plus theta is equal to f of 270 minus theta. So now we are going to discuss about the odd function and also quarter wave symmetry. if any function satisfying these properties, then we will see what is the nature of, then we will see what is the basic nature of the Fourier series transform coefficients are. So if f of theta is equal to minus of f of minus theta, or simply we can say that f of minus theta is equal to minus of f of theta, then we can say that function is said to be odd function. And if you want a quarter wave symmetry, means f of 90 plus theta is equal to f of 90 minus theta, and f of 270 plus theta is equal to f of 270 minus theta. If any function satisfying this property, then we can say that it is said to be quarter wave symmetry. So as if any function satisfying these both functions, then we can say it is an odd function and also quarter wave symmetry. So based on that, what is the Fourier series coefficients are going to happen, we will see. See, odd function I have already told you, a0 is equal to 0 and an is equal to 0. So for odd function, definitely bn is not equal to 0. Only for, as it is a quarter wave symmetry, so only now odd harmonics are going to present. See, it is same for whether the half wave symmetry or the quarter wave symmetry, only the odd harmonic terms are going to present, but not the even harmonic terms. So therefore n is equal to 1, 3, 5 up to infinity, only odd terms are going to present. So then what is the value of the bn? Bn is equal to 2 pi integration of 0 to 2 pi f of theta into sin n theta into d theta. This is the actual way to figure out the Fourier series coefficients of the bn. So now we are going to simplify it into very smaller pattern, which is, as it is a quarter wave symmetry, means you can go only from 0 to 90 degree. So the remaining, so 0 to 90 degree means again 90 to pi, again pi to 3 pi by 2, again 3 pi by 2 to pi, 2 pi. This is overall you have to do, means 4 times, you have to do again 4 times. So into 4 times. So therefore, you can do this one is for easy fashion. For a, you can say that for quarter wave symmetry, because it is only from 0 to pi by 2. The remaining 4 times you have to do the 4 times, so therefore you are going to get the value of Pn. So now let us understand a simple concept through example. So let us understand a simple concept through example. Suppose there is a function like this, f of theta, it's a function of this format. So this is somewhat same to, this is a single phase full bridge output voltage of a single phase full bridge voltage source inverter. So from 0 to pi, its value is plus VDC, and from pi to 2 pi, its value is minus VDC. So now we are going to basically analyze this function. So you can see clearly this function is basically an odd function. So this function is basically an odd function, and also it is going to satisfy the half wave symmetry, because if you delay it by pi, and if you do the inverse, it is again equal to f of theta. So it is going to satisfy the half wave symmetry, and also it is going to satisfy the quarter wave symmetry. See how it is going to satisfy the quarter wave symmetry means here f of 90 plus theta is equal to f of 90 minus theta, and f of 270 plus theta is equal to f of 270 minus theta. So these problems are also satisfied by this function. So we can say that this is an odd function, this is a half wave symmetry function, and also it's a quarter wave symmetry function. All these three things are going to satisfy this function. So now we are going to calculate the Fourier series coefficients of this periodic signal. As I have already told you, for an odd function, definitely a0 is equal to 0, an is equal to 0. So bn is not equal to 0 only for now, only for odd number of harmonics. N is equal to 1, 3, 5 up to infinity. Only odd harmonics are going to present, but not the even harmonics, because this function is satisfying both the half wave symmetry and also quarter wave symmetry. So bn is equal to 2 pi integration of 0 to pi f of theta into sin n theta into d theta. So you can split into whether, so you can split this into whether half wave symmetry or the quarter wave symmetry. You can go for any of the procedure, you are going to get the same result. So you can do over this one also, you can even do this one also, you can even do this one also. All are going to give you same result. So this is a general explanation. But here, as it is going to satisfy the half wave symmetry, we can use even half wave symmetry principle also, which is 2 by 2 pi integration of 0 to pi f of theta into sin n theta into d theta into 2. Or if you want to use the quarter wave symmetry formula, which is 2 by 2 pi integration 0 to pi by 2 f of theta into sin n theta into d theta into 4. You can apply either this principle or this principle or this principle. So everything is going to give you same result. So I can simply say that here only the only odd harmonics of sine terms are going to present. So after doing simplification, finally we are going to get Bn is equal to 4 VDC by n pi. Only for odd harmonics it is going to present. So if you substitute in the general expression, then f of theta is equal to sigma n is equal to 135 to infinity 4 VDC by n pi into sine n theta. This is the Fourier series expression of this periodic signal. So now we are going to study about the voltage control of unequal PWM. So voltage control of unequal PWM. So this is a very important topic. So this is the concept now we are going to study. The voltage control of the unequal PWM. So you can see clearly this is a circuit diagram. So these are the switches, one switch, second switch, third switch and fourth switch. So this is a load. So load basically terminals are A and B. So this is similar to a single phase full bridge voltage source inverter. So then I have already told you VA0 and VB0 are called as the pole voltages, and whereas VAB is called as the line voltage. So we are going to plot all these things. So when the switch 1 and switch 2 is on, so whenever the switch 1 and switch 2 is on, then we can simply say from the diagram VA0 is equal to VDC by 2 and VB0 is equal to minus VDC by 2. So this is the thing that you are going to get. So if you want VAB, which is VA0 minus VB0, so if it is subtraction of these two things, VA0 minus VB0, we are going to get plus VDC. So this is the output voltage we are going to get. Similarly, whenever the switch 3 and switch 4 are on, then definitely VA0 is equal to minus VDC by 2 and VB0 is equal to plus VDC by 2. So if you do the subtraction V0 minus VB0, we are going to get minus VDC. So this is the output voltage or the voltage across the load we are going to get. So this is the diagram that you are going to get simply. So this diagram is the phase shift of this diagram by 180 degree. And similarly, this is the subtraction of these two signals. So now we are going to basically analyze this graph. So I have already told you VA0 and V0 are called as pole voltages, whereas VAB is called as the line voltage or the load voltage. So V0, VB0 and VAB, all these are called as the odd functions, and also it is going to satisfy the half wave symmetry and also quarter wave symmetry. So all these line voltages and the pole voltages are going to satisfy three properties, which are the odd function and half wave symmetry and also quarter wave symmetry. So these are the three properties satisfied by these graphs. So whenever I switch on the 1 and 2 switches, so A is connected to 1 and B is connected to 2, then I already told you VA0 is equal to plus VDC by 2 and VB0 is equal to minus VDC by 2. So VAB is equal to VA0 minus VB0. So we are going to get VDC. Similarly, when I switch on the switch 3 and 4, so A is connected to 4 and B is connected to 3, then VA0 is equal to minus VDC by 2 and VB0 is equal to plus VDC by 2. So VAB is equal to VA0 minus VB0, we are going to get minus VDC. So we have drawn this graph. So I already told you VAB is equal to VA0 minus VB0. Then I want to find what is the Fourier series coefficients of this V0. I want a periodic expression of this V0. So V0 is equal to, I have already told you, basically it is a odd function and half wave symmetry and quarter wave symmetry. So A0 is equal to 0, An is equal to 0, Bn is not equal to 0 only for odd harmonics. So simply sigma n is equal to 135 up to infinity Bn sin n omega t. So if you want Bn, so therefore if you want Bn, let me first find what is the value of B1. Then B1 is equal to, general expression Bn is equal to 2 pi integration of 0 to 2 pi, and here we are going to get, this is f of theta into sin n theta into d theta. This is the general format. But I want only B1, so substitute n is equal to 1. So 2 by 2 pi integration of 0 to 2 pi, here we are going to get f of theta into sin theta into d theta. But as it is going to satisfy the quarter wave symmetry also, so I can split into 0 to pi by 2 into 4. I can do like this. In 0 to pi by 2, what is the nature of the VH0? Here it is 0.5 VDC, therefore 0.5 VDC. So if we do a simplification of this one, finally we are going to get 2 VDC by pi. So finally we are going to get 2 VDC by pi, we are going to get. So B1 is equal to 2 VDC by pi. But I want Bn, general expression, just divide by n, everything is same. So 2 VDC by n pi is the general expression. So therefore n is equal to 135, only the odd values it is going to hold. So simply I can say that V0 is equal to sigma n is equal to 135 up to infinity 2 VDC by n pi into sin n theta. So this is the value of this is the Fourier series expansion of this V0. Similarly, I want to find what is the Fourier series expansion of the VB0 is equal to sigma n is equal to 135 up to infinity 2 VDC by n pi sin of n omega t minus n pi. So because it is delay by pi, so therefore minus n pi. So if you want VAB, it is VA0 minus VB0. So if you do the simplification, finally we are going to get sigma n is equal to 135 up to infinity 4 VDC by n pi sin of n omega t. So this is the thing that we are going to get finally. So this is the expression of these are the expressions of VA0, VB0 and VAB. So now we are going to study some important case 1. So now we are going to study some of the important case 1. So you can see clearly this is VA0. So this is the VA0. I have already told you, whenever say I am going to on the switch, I am going to on the switch 1 and switch 2. So I am going to on the switch 1 and switch 2 from 0 to alpha degree. So from 0 to alpha degree, I am going to switch on from 0 to alpha I am going to switch on the 1 and 2 switch, and what I am going to get, then V0 is equal to plus 0.5 VDC and VB0 is equal to minus 0.0 VDC. So therefore VAB is equal to plus VDC we are going to get. So you can see clearly from 0 to alpha I have switch on the 1 and 2. So if I on the switch 1 and 2, I have already told you V0 is equal to 0.5 VDC and VB0 is equal to minus 0.5 VDC. So VAB is equal to VDC from 0 to alpha. Similarly from alpha to 180 minus alpha. So from alpha to 180 minus alpha, I am going to switch on the switch 3 and switch 4. So VAB is equal to minus 0.5 VDC. So VB0 is equal to plus 0.5 VDC. So VAB is equal to V0 minus VB0. So we are going to get minus VDC. Similarly, from 180 minus alpha to 180, I am going to switch on the switch 1 and switch 2 again. Then I am going to get V0 is equal to plus 0.5 VDC, VB0 is equal to minus 0.5 VDC. So VAB is equal to, we are going to get plus VDC. Similarly, from 180 to 180 plus alpha, I am going to switch on the switch 3 and switch 4. So V0 is equal to minus VDC by 2 and VB0 is equal to plus VDC by 2. So therefore VAB is equal to minus VDC. Similarly, from 180 plus alpha to 360 minus alpha, I am going to switch on the switch 1 and switch 2. So therefore V0 is equal to plus 0.5 VDC and VB0 is equal to minus 0.5 VDC. So VAB is equal to plus VDC. Similarly, from 360 minus alpha to 360, I am going to turn on the switch 3 and switch 4. So therefore I am going to get V0 is equal to minus 0.5 VDC, VB0 is equal to plus 0.5 VDC. So therefore VAB is equal to V0 minus VB0. So we are going to get minus VDC. So this is the graph we are going to get finally. So therefore just by this we are going to switch the things in a irregular manner. So we are going to switching on a regular basis. And finally we are going to get in this graph. So based on switches. So if you turn on switch 1 and switch 2, so VAB is equal to plus VDC. If you switch on the switch 3 and switch 4, we are going to get V0 is equal to VAB is equal to minus VDC. So in that fashion, we are going to get these voltage diagrams. So you can see clearly here the pulse of 0 to alpha, the pulse is different, and from alpha to 180 minus alpha, the pulse is again different. So both are different pulses of different beats. So this is called as the unequal pulse width modulation, because the plus VDC width and the minus VDC width are both are different. So because of this reason only we say it is a unequal pulse width modulation. So now we are going to analyze this circuit. So we are going to analyze this circuit. As I've already told you, V0, VB0 and VAB means the pole voltage and line voltage are simply odd wave, means they are basically odd functions, and also they are going to satisfy the half wave symmetry and also quarter wave symmetry. All these three properties are satisfied by these functions. And also you can see clearly from the diagram that the alpha is very near to 90 degree. Alpha is very near to 90 degree. You can see from the diagram itself, circuit diagram, from the graph itself. So now I want to find what is the value of V0. V0 is equal to, I already told you, for odd function A0 is equal to 0, An is equal to 0, Bn is not equal to 0 only for odd terms, because it is going to satisfy the half wave symmetry and quarter wave symmetry. So sigma n is equal to 135 up to infinity Bn sin n omega t. So I want to find what is the value of Bn. Bn general expression is 2 by 2 pi integration of 0 to 2 pi f of theta into sin n theta into d theta. This is general format. Now I want to do for quarter wave symmetry. So therefore I am going to split into 0 to pi by 2 into 4. So 0 to pi by 2. So 0 to pi by 2. So 0 to pi by 2 I can split into two parts integration from 0 to alpha and from alpha to 90 degree. So 0 to alpha its value is plus 0.5 EDC, and from alpha to 90 degree its value is minus 0.5 EDC. So after doing the simplification of this one, finally we are going to get B1 is equal to 2 VDC by pi into 1 minus cos 2 alpha. So this is the value of B1 we are going to get, which is 2 VDC by pi into 1 minus 2 cos alpha. Now I want to find what is the value of Bn general expression divided by n, that's it. So 2 VDC by n pi into 1 minus 2 cos n alpha. So divided by n, and here keep n alpha. So Bn is equal to 2 VDC by n pi into 1 minus cos 2, 1 minus 2 cos n alpha is the value of Bn. So you can substitute in the general format. Finally we are going to get V0 is equal to sigma n is equal to 135 up to infinity 2 VDC by n pi into 1 minus 2 cos n alpha into sin n omega t. So this is the value we are going to get. So whereas VB0 is just phase shift of pi degree. So therefore sigma n is equal to 135 up to infinity 2 VDC by n pi 1 minus 2 cos n alpha into sin of n omega t minus n pi. So just by shifting, the Fourier series coefficients are still same. The only thing is we need to shift by pi. So VAB is equal to sigma n is equal to 135 up to infinity. Here 4 VDC by n pi 1 minus 2 cos n alpha into sin n omega t. So only thing is here the Fourier series coefficients are same. Whether means it is just the same value we are going to get. Only thing is here sin n omega t. So VAB is equal to sigma n is equal to 135 up to infinity 4 VDC by n pi 1 minus 2 cos n alpha into sin n omega t. So basically now I want to find what is the peak value of the fundamental component of the V0. So I want to find what is the peak value of the fundamental component of the V0. So the substitute n is equal to 1, we are going to get 2 VDC by pi 1 minus 2 cos alpha is the peak value. Suppose if alpha is equal to 60 degree, so alpha is nearly equal to 60. So if alpha is nearly equal to 60, so alpha is nearly equal to 90. So therefore now, suppose if alpha is equal to 60, what is going to happen? If you substitute alpha is equal to 60, we are going to get a peak value as 0. And if you substitute alpha is equal to 90 degree, and if you substitute alpha is equal to 90 degree, we are going to get the fundamental peak value is 2 VDC by pi. So when the alpha is lying between 60 degree to 90 degree, the peak value of the fundamental V0 value is going to lie from 0 to 2 VDC by pi. So as alpha is nearly equal to 90, so therefore if alpha is lying from 60 degree to 90 degree, the peak value of the fundamental output voltage of V0 is going to lie from 0 to 2 VDC by pi.